morning, guys. So yesterday we left off with this question here. We started looking at acceleration, which was how quickly your speed itself changes. In this problem here, we have our object is a bike. It's going to slow to a stop, so we had said that the VF is equal to 0. We end up coming to rest. It decelerates. Remember, deceleration is basically another way of saying negative acceleration. And essentially, whenever your speed, whenever your direction, I'm trying to head in one direction and the acceleration is against me, that's going to cause a deceleration. So if we assume that, let's say, velocities are positive going to the right, we actually put in the negative just to imply negative. So that will basically mean after every second, I lose 2.4 meter per second. And I do that for 6 seconds before I come to a stop. Like we ended off here, we just drew a picture here. It might be helpful to just list the variables as we have them, because as we get to our equations, you're just going to essentially put these numbers in. So acceleration is going to be negative 2.4. The time that we're going to slow down over is 6 seconds, and then we have 0 meter per second. Let's first calculate the initial velocity. So initial velocity, so far in our equations, we have VF is equal to VI plus AT. You do have all these formulas and the ones that we talk about today on your formula sheet. And all you're going to do is you're just going to plug through the values. So the VF here happens to be 0. We don't know what your starting speed is, but we know that you lost 2.4 meter per second for every second, and you did that for 6 seconds of time. So 0 is equal to VI plus 2.4 times 6, so it's going to be negative 14.4, and when I bring that over, it then gives me 14.4 meter per second VI. Just to put that number in context here, right, so that is after every second you're traveling 14 meters, which is actually quite fast. If you multiply that 3.6 just sort of roughly in your head here, this is about 50 kilometers per hour. So this bike here is definitely zipping along. We sort of ended off with a question here, well, what about the distance? I know I do cover some positive distance. Yes, I know I'm going to slow down, but it takes me a little bit of runway to actually stop. So the displacement that I'm expecting here is going to still be positive. It's not like we just sort of come crashing to a halt right away because I decided to decelerate. We just sort of gradually bring ourselves to a stop. Here's the issue is because there actually is an acceleration, your displacement is going to depend on acceleration. Now, the first way we're just going to start thinking about it before we actually get to our equation here is, well, at first, we're saying this bike here, let me just draw another picture here. At first, this bike here is traveling at 14.4 meter per second. Let's say it travels 14.4 meter per second for 6 seconds of time, right? Let's say there is no deceleration. So I just go velocity times time. That's going to equal to 86.4 meters, right? So if I had my initial speed that we just calculated, if there was no slowing down whatsoever, it's going to end up as 86.4. The only problem here is from the moment that I start the clock, my speed actually starts slowing down. So a second later, maybe we're like 12 meter per second. A second later, now we're only down to 9 point something meter per second. So the speed is constantly changing to the extent that at the end of the day, we are actually traveling at 0 meter per second. Let's say we do that for 6 seconds, that we actually get 0 meters. Fortunately for us here, we're going to assume, right, this is always an assumption of ours here, we're going to assume that the acceleration is constant over the distance. And this is always what we're going to assume. So unlike the very first kinematic problems that we did where I was traveling at one speed for a shorter time and I travel at a different speed at a longer time here where I couldn't take the average velocity, this time I can actually do an average velocity. This time I can sort of think about this, well, I know realistically you're not going to stay at 14.4 for long. You only make it to 0 at the really, really end. What if we just took an average between the two? What if I said you went, let's say 0 plus 14.4 divided by 2, so that's going to be about 7.2 or so. The 7.2 going forwards would actually be slower than the first part of the motion, right? I'm actually traveling faster than 7.2 at the beginning, but then afterwards, it's going to actually be slower than 7.2 here. The 7.2 is a nice average, it's a nice approximate value. Because the acceleration is constant, we can call it uniform acceleration. I can sort of think about it this way here. I want to do displacement is equal to speed times time. That's what I did with 14.4 times 6 to get this 86.4. But this time, because my speed is changing, I'm actually going to punch in V average. We're not going to deal with this particular formula too much, but V average essentially says because the time intervals are even and because we're constantly slowing down, we could just simply take this as VI plus VF divided by 2. Just a simple average. We can say my starting speed here was 14.4. My ending speed here is 0. on average, that's how I got my 7.2. Let's pretend we go at 7.2 for the duration of these 6 seconds here. And we'll see what we get here. We punch in an average velocity of 7.2. Again, the 7.2 would be slower than the first half of your slowdown interval, and 7.2 will be faster than the latter half here. We're hoping the 7.2 is some nice middle ground here. If we did that speed for 6 seconds, that's actually how we can calculate the displacement. 7.2 times 6 is equal to 43.2 meters. So I just want to introduce, there is a way of reusing this basic motion equation, d is equal to vt, but the value in here has to be the average velocity because the speed is always changing over the course of this motion here. Now that one here is a little bit, you need to think about it, because we have to think, okay, well, what's the average speed between the two? What if we sort of pretended, well, this middle speed here is slower than the first half and it's bigger than the latter half here? What I'm going to do in today's lesson here is I'm going to give you the two other kinematic equations. It'll get us back to this 43.2. We'll verify that, but without really us having to think about, oh, is this average velocity? Effectively, the math actually does this as well, but it's just framed in a slightly nicer way of doing it. So let's just continue on with our lesson for today here. These ones here are called our kinematic equations. These are our equations of motion. So far, we've actually seen two equations. So in the order that we saw them, we just alluded to this one here. Our basic motion equation. Basic motion implies that there is no acceleration, that velocity is constant. We basically said your distance is equal to speed times time. Or if you want the vector equivalence here, displacement is equal to velocity times time. As long as there's no change in direction, you can the vector and the scalar form will be the same. This one here actually came from the definition. So this was the definition of velocity, if you want to look back at that lesson there. So it's just slightly rearranged there. Velocity was how far you get versus time. I rearranged the variables here. If I know this is my speed, and you multiply it by how long you actually travel at the speed here, assuming that the speed is constant, we have this situation. Now what we did in this lesson is we said, okay, yes, of course, if velocity is constant, that's nice, but especially in the case of a changing speed here, you could think of this here as an average velocity that doesn't change, and you can sort of think about it that way. But in some sense here, I just leave that just by itself, d is equal to vt. We're going to come back to that formula in just a second here. The second equation we dealt with here is, there's no real name for it, but it actually came from the definition of acceleration. In fact, the next two formulas that I give you will all involve acceleration. So how I'll separate it here is I'll usually say, if there's no indication there's acceleration, just use equation number 1. Because that one there, your average speed is basically the speed that you have for the entire motion. If you have acceleration, you're down to 3 other equations. From the definition of acceleration, let me just repeat this for you here. We did acceleration is a change in velocity over a change in time. We had rearranged that, again, you can see yesterday's lesson here. We had rearranged it to form Vf equals Vi plus At. Basically, my ending speed would be identical to my initial speed as long as you didn't have any acceleration. If you do have acceleration, it tells me how quickly my speed changes. I multiply it by time to figure out what's the total amount your speed changes. Your Vi plus the amount your speed changes gives you your Vf. That's what that formula tells you there. Today, what I'm going to introduce to you, like I mentioned, are 2 new equations. This third equation that we're going to deal with, it actually is the basic motion equation, but it's the basic motion equation if there is acceleration. So let me just list this equation for you here. This third basic motion equation here is d, your displacement, is equal to VIT plus 1/2 AT squared. Again, it's on your formula sheet. I'm not expecting you to memorize it, but given sort of a problem, you can list your variables and you can plug in the numbers as you would normally. So that's our equation there. So a couple notes here. It's very similar to our first equation. In fact, we'll actually derive our first equation again. We have our displacement, our how far. Sure, it depends on speed times time. The difference here is this time, because I know there is going to be an acceleration, this time I'm going to introduce this as initial speed. So this is sort of like going back to our earlier problem here. Well, I know I was at 14.4. I know from the second I start my clock, my speed starts slowing down. I'm just going to take the V initial, which is 14.4, times it by the time. What would have been the total velocity? What would have been the total distance if my speed actually didn't change? So that's what this is saying. If my 14.4 was done at 6 seconds here, that would have given me my total distance. However, in this case here, because I had an acceleration, my acceleration here is actually negative. This is going to end up multiplying to become a negative number. This is going to take away some of that distance I could have gotten if I traveled at this speed for the rest. What I want to show you in this formula here is, in fact, equation number 1 is actually a slightly simplified form of equation number 3. In fact, we're just going to use this terminology here because equation number 1 here assumes no acceleration. No acceleration in math here is I'm going to put in a is equal to 0. What if a is equal to 0 in this formula? So if there is no acceleration at all, if a is equal to 0, 0 times this entire term just becomes 0. This entire term here just drops out, and we just simply get d is equal to vt again. So that basic motion equation that we had introduced at the really beginning here is actually just a slight simplification of the third formula. Of course, in cases like this where we have an acceleration, we will definitely keep this half at squared term. So just to verify this formula works, just to make sure somewhere along the way it actually calculates an average velocity inside of it, let's see if we can calculate again. What is the displacement? Without us actually doing the average velocity, let's see if we can get the same 43.2. So here what we're going to do is we're going to say your displacement, your initial velocity I believe was 14.4. We're going to decelerate over 6 seconds. So again, that's the total amount of distance that you get, plus 1/2. The deceleration was negative 2.4. After every second, I'm 2.4 slower than I was to begin with. And this time it's multiplied by a t squared. In this formula, it's only that's t that's being squared there. Right. So I'm going to punch through this math here. Let's just verify we get that 43 number back. 14.4 times 6, this is the earlier number I got. If there was no change in speed at all, I should have been able to cover a ground of 86.4. However, because there is a deceleration, this is actually going to take away some of that distance. Because I don't stay at 14.4 for long, I actually gradually get less and less. So let's go 0.5 times negative 2.4 times it by 6 squared. This is actually going to remove from me half my velocity, 43.2, and that gives me here a total distance of also 43.2. So just to verify, even though this is sort of a new kinematic equation, it's sort of a more thorough version of the basic motion equation that we did, but factoring in acceleration, we got 43.2, and that's what we had calculated earlier. From this point forwards here, we don't really need to use this average velocity formula anymore, because I actually have it in this formula. It's actually framed out. If you know the acceleration, just plug in that number there, and this will give you the total displacement. All right, I'm going to prove to you one last formula. So far this is nice. I have two main formulas that work with acceleration. This one deals with VF, VI, as well as time. This one factors in the displacement aspect of it. What I'm going to do here is I'm going to put these two equations together. I'm going to combine these two. So let me just show you how I'm going to derive the fourth expression. You never need to repeat this derivation here. This the final answer is just on your formula sheet itself. I'm just going to show you where this comes from here. I'm going to take the formula that we knew from earlier. VF is equal to VI plus AT. Take this new full form D is equal to D is equal to VIT plus 1/2 AT squared. And essentially what I want to do is I want to put one of these equations into the other equation here. So what I'm going to do here seems a little bit crazy. I'm going to start on the left side first. What I'm going to do here is I'm going to square both sides. Right? Nobody's telling me to do this, but essentially as you walk through the math here, you'll see what we're doing. So I square both sides. In this case here, I'm actually going to get a v final squared. This part you need to be careful. It's a binomial that's being squared. Right? So it's not just going to be vi squared, h squared, t squared. It's actually that thing multiplied by itself. If you think about that one there, if I have a binomial multiplied by a binomial, you may have learned in your math classes, oh, we actually need a FOIL. We actually need to do something like the first things get multiplied, vi times vi gives you vi squared. Then we go the outer, right, vi times at. The middle term here is also vi times at, so that's going to pull out a 2 vi times at. Remember, I is a subscript, just to remind you that it's the initial velocity that we're using here. And then we're going to get an at times at, which gives you that expected term a squared t squared. Right? What I'm going to do now is I'm going to just leave the vi squared term out. I'm noticing that in this sort of latter part here, I'm noticing that there's an a in both terms, and I'm going to pull out this 2 here. What I'm going to do here is I'm actually going to factor out the a term. Sorry, not even the 2. Just factor out the a term. This gives you here 2 vit, again, you never need to repeat this, as at squared. And then now we're just going to match this up. using our other formula now, we're seeing a lot of similar terms. We're seeing a VIT and we're seeing a half AT squared. This is just a slightly sort of scaled down version of this one here. What if I multiply both sides by 2? So in that case there, I'd actually end up with 2 times displacement is equal to 2 times VIT plus half AT squared, like that. Or if you like, you can just multiply that 2 in. That would be 2 VIT. That 2 times the half would actually get rid of the half. And now I have an exact match. Wherever you see 2 VIT plus AT squared, I can actually punch in 2D. Well, I see that term right here. I'm going to punch in 2D for there. So effectively what we're doing is we're taking two independent equations, right? This is one formula, this is another formula here, and I'm just rearranging the variables. I'm putting this second formula here into the first formula, and now we end up with our last formula here. We see that it came from sort of the combination of the two of them, but this is your final formula. The VF squared is the VI squared. I'm going to pull that 2 in front of the A there, 2 times A times D, and this becomes our fourth kinematic equation, right? So if you look on your formula sheet here, we actually have these four kinematic formulas here. You might find on your formula sheet here, I've been using VF and VI just for simplicity, right? F stands for final, and then VI, right, is initial, right? I've been using that just to make the lettering a little bit easier for you. On your formula, let's say for this equation here, you actually see it usually in textbooks. It's formatted here just V squared, and then V naught squared plus 2AD. They're just switching up the notation a little bit for you here. In physics, there's a lot of times that we deal with sort of initial conditions. And for initial, we usually use this tiny little, it's almost like an O symbol. This is a naught symbol. And that naught actually implies initial velocity. So if you see that naught anywhere, it typically means initial. And seeing as I use that naught symbol for initial, then I don't need to say VF. The one that doesn't have a naught here, that 0 there, we're going to say it's a final velocity. So you can continue using the VF and VI, no problem. I just wanted to make that note here on the formula sheet. You'd actually see it written in that fashion there. So let's just practice using these kinematic equations here. Okay, so in this problem here, we have a plane accelerates at 10 meters per second down a runway for 20 seconds. I want you to calculate, let's actually say from rest. So I'm going to give you the initial speed. It's not always going to be 0, but in this case here, we're starting at 0. I want you to calculate for me here, calculate the final velocity. I know it's going to be sort of speed up and actually get ready to take off. Calculate that final velocity and the displacement. Calculate how much ground does it need to actually get up to that speed there. So as usual, what I try to do here is just start off with a picture. So we have our plane. Our plane here, it's starting from rest. So I can list for me here, the V naught is equal to 0. I use the new notation there. It's going to start accelerating at 10 meters per second squared. So this time I know my A is actually equal to 10 meters per second squared. Upon every second, I'm traveling 10 meters per second faster than it was. Let's say this is 0 seconds. I'm at 0 meters per second. In 1 second of time, the plane is going to start traveling at a speed of 10 meters per second. At 2 seconds of time, it's actually going to travel up to 20 meters per second. What I want to show you in this picture here is, you'll notice acceleration gives me, after every second, I have increased by 10 meters per second. I'm 10 meters per second faster than I was to begin with. But you'll notice distance-wise here, you're actually going to cover more ground. If in the first time interval I'm going from 0 to 10, I'm not going to cover as much ground. At 1 second beginning there, I'm already traveling at 10. As I increase by that 10 meters per second, I'm still going to go 10, 11, 12, 13. I'm going to cover much more ground even in the same time interval. And I'm going to do that for 20 seconds worth of time until I finally am ready to take off. We're interested in calculating the final velocity. So what's your final speed over here after 20 seconds, and calculate sort of what's the length of this runway? How long does this actually sort of stretch over for me to actually get up to the speed here? As you look at your kinematic formulas here, let me just make a list for you there. First thing I would do is I would ask myself the question, is there an acceleration? If there is an acceleration, I would not use the basic equation. The basic equation was basically d is equal to vt, right? That one there, I need to do with that funny business here with average velocity and no acceleration. If there is an acceleration, I'm down to using the other three formulas. From the definition of acceleration, so just make a note to yourself here. If there is no acceleration, you're more than welcome to use d is equal to vt. But if there is an acceleration, we have to look at one of those three other equations. And in this case here, if there is an acceleration, let me just list all of them and we'll make some notes here. V is equal to v naught plus at, that's one formula. The new formula d is equal to v naught t plus 1/2 at squared, somewhat more thorough version than the basic motion equation. And then when we had put these two equations together, we had v squared is equal to v naught squared plus 2ad. All of these formulas here are written for you on the formula sheet. We'll know we can use an equation if I know all the variables except for one unknown. So usually what I tell people as you're learning this here is just make a list of variables, and you can just get a sense of sort of which formulas I can use. In this case here, we've already labeled here v naught is equal to 0, so I have a v naught. Let me highlight that for you. So I have a v naught, I have this term. I have the time, right? The time is going to be 20 seconds, so I'm going to highlight that one there. I have the t term, right? So if I need it, I can punch in the t. And I know the acceleration, so acceleration is actually 10 meters per second squared. I actually know a. Looking at the values that I've sort of highlighted, I can say, well, I can use either the first equation or the second equation. I know I started from rest, I know how quickly I speed up, I know how long I speed up for. This is actually going to help me find my final velocity. Great, right? I know all the unknowns. It's even isolated for the v here. And if you want to find the displacement, I can simply punch into this one because I have all these other numbers. I can find the displacement. In fact, if you just make a general comparison of these formulas here, you will notice that the first formula and the last formula here, they both deal with final velocity. So if the question either gives you final velocity or is asking for final velocity, you will need one of these two equations. This first one frames it in terms of time. It doesn't really care about displacement. I'm leaning towards that one there because I don't know the displacement just yet. And even if I calculate a displacement, in case my d was wrong, I don't want that knocking out my final velocity. Just use the time that I'm sure about that was given in the question. If I was given a displacement and I was not given a time, I know it's just sort of, it takes this much room for it to speed up. I don't know how long it took. This formula here doesn't deal with time at all. And this middle one here is sort of some compromise between the two. It doesn't deal with final velocity at all, but it links between time and displacement. But all three formulas sort of work interconnected. They work hand in hand. Based on our observations here, we probably want to use either the first equation or the second equation here. So let's just punch our way through here. We know we're starting from rest. We know my acceleration rate is 10. After every second you're 10 faster than you were to begin with, I multiply it by 20 seconds, and now I'm going to actually be at a speed of 20 meters per second. I gradually increase from 0 upwards to 200. Let's try that mid equation to get the displacement then. I again start from rest. I travel for 20 meters per second, 20 seconds, but times 0 just kills off that term. Plus 1/2, I'm going to speed up at 10. Again, it's going to be multiplied by 20 squared here. And then we're going to have a look at, well, how much ground, how much runway did I need to speed up over? Right. So I multiply just that last term there, 0.5 times 10 times 20 squared, and this gives you here 2,000 meters. Right. So we've been able to answer the question here just for a double check, just to make sure not only are these formulas consistent with each other here, consistent that these numbers here work out. I can pretend to test for another variable. Let's pretend, oh, I don't know the v final squared. Let's just practice. So in this question, I actually didn't need this formula. But just for practice here, if I gave you a starting speed of 0, you square 0, it's still going to be 0. Plus twice, your acceleration is going to be 10. And if I had calculated, oh, your runway has to be 2,000, I multiply by 2,000. So we get here 40,000. This is not your final velocity. This is the final velocity squared. We still need to square root this to get the final velocity. The root of 40,000 gives you here 200 meters per second, and at least is consistent with the earlier problem. All right. Let me practice for you one other formula here. Your worksheet here will have a lot of these motion setups here. Make a list of the variables and just start practicing, getting familiar with using these equations. We'll go from there. So let's end off with this one here. I'm going to have a truck. Truck decelerates from 80 kilometers per hour to 20 kilometers per hour. So I have a starting speed and an ending speed here. over a distance of 50 meters. I want you to calculate the acceleration and the time. So let me just hint at how you're going to do that there, and I'll leave it for you to practice here. First thing you're going to notice here is, although we're given two speeds, right, we decelerate from this speed here. This is my v initial, this is my v final here, or you can say v and v naught. The problem here is both of these are not in the correct SI units. The SI units for speed is supposed to be meter per second. Remember, we did the conversion here. Imagine dividing this number by 3.6. You don't need to show all those fractions and everything. As long as you remember it's 3.6, 80 divided by 3.6. When I make a list of variables, I would actually say my v naught, my v initial is actually 22.2 meter per second. My v final is 20 divided by 3.6. So that gives me 5.56. Make sure everything is in SI units before you actually go and solve for it here. We actually have the displacement, right, or the distance. Right? There's no change in speed. I'm just gradually coming to a stop. That's 50 meters. And the question here is, well, what's the acceleration, right? After every second, how much speed have I lost, and how long did it take to do that? So we have our picture. We knew it was 80 kilometers per hour, but I'm actually going to track it as we were going 22.2 meter per second. Later on, I'm traveling a little bit slower. This is 5.56 meter per second. We cover a distance. It takes this much. Again, what's important for you to realize in this question here is, even though, yes, we are slowing down, right? So we'll do this more in the next lesson here. Remember, whenever your velocity is trying to head one way, but the acceleration is going against you, acceleration should come out to be negative here. It's not like we just sort of stop in our tracks and suddenly come crashing to a halt. It does still take some positive distance for me to actually come to a stop. And in this case here, it actually takes me 50 meter to gradually glide to a stop. I'm steadily stepping on the brakes, so I know the v, not the v and the d. And your goal here is to find the acceleration and find the time.